let us move on to the next module. I am going to define another notion called regular sequence. Okay. So, what do I mean by regular sequence? A sequence of good functions, let us say I denote by that sequence as f n of x. A sequence of good function is regular if for any good functions g x I have the following integral f n of x g x dx, this exists, right. So, if I can integrate with respect to this good function g x, if I can integrate the sequence of functions f n x and they exist, then this sequence is called regular functions, right. Well, to give you an example, if I have this function f n given by phi x of n, right, where my phi x is a good function, right. So, then what do I get? This integral of minus infinity to infinity f n times g, well, in this case g's are phi, right. Well, let us say for a general g. So, f n of g dx, I get this equal to 1 by n integral minus infinity to infinity phi times g dx, right. So, this is a good function, integral of two good functions, integral of the product of two good functions will also exist. And then as well, I need to mention that this integral should exist in the limit n tending to infinity, right. So, what happens in this limit? In this limit I get, for this example, as I take the limit, the integral goes to 0. So, as my n tends to infinity, the integral tends to 0, because the numerator, in the numerator the integral exists, right, because it is a product of two good functions. Okay. So, then I need to define some equivalence. Let me call this expression as my expression 4, right. So, I am going to call this expression as expression 4. So, two sequences of good functions are equivalent if my 4 exists and are identical for both sequence, right. So, when I am going to compare two sequence of regular functions, right, well, two sequences of good functions, I am going to compare their corresponding integral which was defined by 4. Okay. Then what I have is that my generalized function. So, that is the thing that I wanted to define to begin with. My generalized functions, let us denote it by f. My generalized functions are defined in terms of their action on integrals of good functions, right. So, what do I mean by that? If I have this function f and I am using this bracket notation, and this is defined as follows. So, this bracket of f comma g is actually the integral from minus infinity to infinity f times g dx, right. Now, since I have this generalized function, so the generalized function is also it is a regular sequence of good function. So, I am going to replace my f as limit n tending to infinity, integral from minus infinity to infinity fn g x dx. So, these are my sequences of good functions, right. So, I get that this is also equal to limit n tending to infinity bracket f n comma g. So, my action of f on g is defined in the limiting sense of f n on g, right. So, this is how I define my generalized function. Okay. So, then finally, I want to introduce the so called ordinary functions. So, if my function f is ordinary, it is also, when I say ordinary functions are your regular functions. Well, ordinary functions are your normal, the functions that you have, or the functions which are so called single valued functions, the functions that we are all aware in calculus. I am going to denote it by ordinary function, right. So, if a function is ordinary, then what I have is that the generalized function equivalent. Let me just highlight all these notations, and I am going to tell you why all these notations are being introduced. So, the generalized function equivalent for an ordinary function, generalized function equivalent for an ordinary function is a sequence of good functions. It is a sequence of good functions f n of x such that for any good function g, I have the following integral true. So, I have that limit n from minus infinity to infinity f n of g dx is equal to your integral from minus infinity to infinity f times g dx. So, whenever I want to highlight, so if I have an ordinary function, so notice where this definition makes sense. So, if I have an ordinary function and I am not able to find the Fourier transform of that ordinary function, then what I do is I represent that ordinary function into this generalized function equivalent using this following sequence, and I am able to find the Fourier transform of that generalized function, and then I take the limit n tending to infinity, and that will give me the Fourier transform of that ordinary function in the generalized sense. Okay. So, I will show you with an example. So, let me just give you one quick example. So, if I have a unit function, I denote it by I of x, right, and it is defined by integral from minus infinity to infinity I of x g of x equals infinity to minus infinity to infinity g of x dx. So, it is an identity function, and its notation is that it is just like multiplication with a 1. So, where g is a good function, right. So, then what I have is that my regular sequence, consider this regular sequence, my regular sequence of good functions which is given by exponential minus x square by 4 n, right. Well, it defines this regular sequence, it defines my unit function, which is the generalized function equivalent to the ordinary function f is equal to 1. So, here I know what is the, I am easily able to find the Fourier transform of f equal to 1. However, suppose if I had a function for which I was not able to find Fourier transform, then the idea is to use the corresponding sequence of good functions. Here in this case it is this one, and I am able to find the Fourier transform of this sequence and take the limit n tending to infinity in that integral. So, that is going to give me the Fourier transform of the ordinary function, corresponding ordinary function. So, similarly, another example is if I have the Heaviside function. So, h of x, it is defined by this following generalized function equivalent, h of x g x, again without loss of generality, these are good functions, right. This is given to be, as the definition says, 0 to infinity g of x dx, again using my Heaviside function. So, this is the generalized function equivalent, of the ordinary function h of x given by 1 if x is positive and 0 if x is non positive. Okay. Let us move ahead. So, well, there is one more example which is of our importance, that is the so called sine function. So, what is sine function? So, the sine function is defined to be plus 1 if x is positive and negative 1 if x is negative. So, this is my ordinary function, this is the ordinary function that I am talking about, the sine function. The generalized function equivalent will be integral from minus infinity to infinity sine of x g x dx, which is, again we replace what is sine of x. So, from negative infinity to 0, sine of x is minus 1. So, I have a minus sine g x dx, plus from 0 to infinity I have a plus sign. So, this becomes plus g x dx, right. So, for this ordinary function sin x, the generalized function equivalent definition is as follows. So, it is the action on this good function g x, right. Also please check this useful relation that sine of x is actually equal to 2 times Heaviside function minus my unit function. So, I am going to use this relation quite frequently. Okay. So, why I have introduced all this notion of good function, generalized function, is to go through the example that I am going to describe next. Okay. The most important example that we have, for which we do not have a proper definition of Fourier transform, is the Dirac-delta function. What is Dirac-delta function? Well, we all know, most of us we know what is Dirac-delta function. So, it turns out that Dirac-delta function is not a classical function, although it is quite heavily used in physics, chemistry, biology, applied mathematics, everywhere. It is not a classical function, right. And well, it is also a function. Well, I can only define this function in the generalized sense. So, it can only be defined in the generalized sense. Why? Because I know that this integral delta of x times 1 dx is equal to 1. So, here my 1 is my good function, right. So, in the generalized sense, my delta function is a function that can be defined, right. And also what we have is that there is no ordinary function, whose generalized function is defined above, right. So, what I mean to say is that my delta function is only defined, well, we all know what is delta function. So, delta function is going to go to infinity at a particular point and 0 otherwise, but as such it is not a function in the classical sense, it is only function in the generalized sense as defined by this integral, and there is no ordinary function whose generalized function equivalent is defined here. Okay. Now, we are quite familiar with some of the properties of delta function. So, again let me just highlight some properties of delta function. Again, these properties are defined in the generalized sense. Okay. So, the one of the properties says that suppose you have a function, let us say a good function, times delta of x minus a, that can also be given to be equal to f of a delta of x minus a. Again, to see this equality, I have to look at this equality in the generalized sense, that is in that integral that I have defined here. Then another property that I have for delta function is x times delta of x is 0. Then I have delta of x minus a, it is an even function. So, delta of x minus a is delta of a minus x, and finally, it turns out that the derivative of my Heaviside function is the delta function, right. So, I am going to prove, I am going to show it later soon. Okay. So, the properties, these are some of the properties that are highlighted, and before I move ahead, I want to mention that I can always approximate my delta function as a limit of the following ordinary functions. So, I can always approximate my delta function as a limit of this sequence. What is the sequence? The sequence is delta n of, well, let me just say delta of x, which is limit n tending to infinity delta n of x, which is limit n tending to infinity. So, these individual functions delta n to be defined as square root n by pi e to the power minus n x square. So, as my limit n goes to infinity, these functions delta n goes to my Dirac-delta function. So, either I can represent my delta function as this sequence, or I can represent my delta function in the generalized sense, that is in terms of that integral representation. Okay. So, let me just show you some cases or some properties of delta function applied to Fourier transform. So, in particular, if I were to evaluate the Fourier transform of delta function, let us say Fourier transform of delta of x. So, if I were to use the definition, this becomes 1 by square root 2 pi negative infinity to infinity e to the power negative I k x delta of x dx. Now, from negative infinity to infinity, I have that there is only one point the delta function attains a non-zero value, and that is at x equal to 0, and at x equal to 0 this is 1, right. So, all I am left with is the factor 1 by 2 pi, right. So, the integral is just 1, right. Conversely, if I were to evaluate the Fourier inverse of 1 by 2 pi, then that is my delta function. Okay. So, why I am denoting this is because this particular definition is used often in physics or quantum mechanics. The definition of delta function as an inverse of Fourier transform. Okay. So, then let us move ahead. Let me just give you a few more properties of generalized function. So, if I have generalized function equivalent, I am going to show you the generalized function equivalent of delta function, right. So, which means I have to define it in terms of a good function. So, for a good function, g x, I have this bracket delta of g, delta comma g, which is defined to be this integral from minus infinity to infinity delta of x g x dx, which is nothing but g at 0, right. So, that is my generalized function equivalent of delta function. Okay. Then if I have to figure out the derivative of the generalized function, let us say I denote it by f prime. So, then again using my bracket notation, f prime g is equal to integral from minus infinity to infinity f prime g dx, right, and I use my integration by parts. So, integration by parts, then I am going to use this as my first function, this as my second function. So, f integral g minus, well, I am going to use this as my first function, this as my second function. So, I get g f evaluated at minus infinity to infinity and then minus integral f g from minus infinity to infinity. Now, this, the fact that the functions are absolutely integrable, because otherwise the Fourier transform would not have been defined, I get that these vanishes at the end point minus infinity and infinity, because these are absolutely integrable functions. So, I get that this is negative integral f g dx, or this is also equal to negative bracket f, well sorry, this is f times g prime, properly using the integration by parts. So, f times g prime, I get the bracket f comma g prime with a minus sign outside. Okay. So, if I were to figure out the derivative of a generalized function, it is negative times the bracket operator operating on the derivative of the good function. Okay. Why I am using this is because I have the next example in mind. So, if I want to show, in this example I want to show that the derivative of my Heaviside function is the delta function, right. So, how to show that? Notice that if I were to use again the bracket notation, so derivative of the Heaviside function applied on a good function, right. So, this is integral minus infinity to infinity h prime of phi dx, and then again using my definition described earlier, this is negative infinity to infinity h of phi prime dx, right, and of course using my definition of Heaviside function, this becomes negative from 0 to infinity phi prime dx. Now, this is derivative of phi and this is integral of phi. So, all I get is a simple integration phi of x evaluated at, well, with a minus sign, evaluated from 0 to infinity, right, and then I get this is equal to phi at 0. Well, it vanishes at minus phi at infinity. Well, this one vanishes because phi is a good function, right. So, I get, well, I know that phi of 0 is nothing but the delta function operated on phi, you can check that. So, I have that the bracket of h prime action on phi is delta action on phi, which means what I get is that h prime is delta, right, in the generalized in the generalized sense. Okay. Okay. Then there is one more example I need you to see. The derivative of the absolute value of x, right. This is also, you can check that this is the derivative of x times sine of x, right. You can check that this is indeed the case. So, so we can use our product rule here, well, with some caution. The product rule has to be used with some caution here. So, this will be equal to x times d dx sine of x plus sine of x dx dx, right. So, then this is 1, and you can check that my sine function is 2 times Heaviside function minus the unit function, right. So, all I get is this is x times 2 times Heaviside function derivative minus the unit function derivative plus sine of x, right. You can check that this one goes to 0, please check that, and this one is nothing but the delta function, right. So, I get this is 2 times delta function times x plus sine of x, right, and I know that delta x times x, this also goes to 0 by the property of the delta function. So, all I get that is that the derivative of mod of x is sine of x. Okay. So, let me just wrap up this lecture by highlighting few of the lemmas that are useful. There is first lemma, the Fourier transform of good functions exists. The another lemma or result that is useful is Fourier transform of good function is a good function, right. Why I am showing you these lemmas is because to help you to evaluate Fourier transforms of ordinary functions where they are not, where you are not able to evaluate them. So, represent them in terms of good functions, right. And if I have, there is one final result which tells us that if I have the Fourier transform of the good function, then the corresponding Fourier transform of the generalized function also exists, right. So, if you are able to show that the Fourier transform of the good function exists, then the corresponding generalized function also exists. So, thank you very much. So, I end this lecture at this point.